Hi everybody. Several people were interested in me discussing the several ways that we've talked about so far for understanding or visualizing parametric curves. So here's a whole series of them that were on the Salmon sheet of paper, and I'm just going to talk my way through them. So we said that one thing that you can always do if you're uncertain is make a data table. So something like the following. You can plug in different values for t. It's important to remember that t can take on all real values, not just positive integers, and not even all of the integers. But if you sort of think your way through this, you can say, all right, so if I plug in 0 for t, that's going to give me 0 for x, and then 1 would give 1, and this would give 4, and this would give 1. And then same thing, if I'm plugging in t values here in the y equation, I would get 0, 1, 2, and then negative 1. And then once you've used t to generate the xy coordinate pairs, you can plot them. So that's one way that's always available to you. But I've said a couple times that I want you to branch beyond that. So here's a different thing that you can do. If it's one that's as simple as this, you could try and combine them together by eliminating the parameter t to produce a regular Cartesian equation. So in this case, I know that y is the same as t. So if I wanted to, I could replace the t in this equation with y, because I know they're the same. So that would give me that x equals y squared, which is the same thing as saying y is plus or minus root x. And that's assuming that t is ranging over all real values. So let's do a little sketch of that. But I'd also said that there's another way to visualize these, and that's by thinking about how are the x-coordinates changing with time, and just imagining that, and then how are the y-coordinates changing with time, and then imagine both of those things happening simultaneously. So let's look at that approach and see why it's going to give us this same picture in the end. So here I've made graphs of the equation for x in terms of time and the equation for y in terms of time. So here, this axis is the t-axis, and the height of a point at a particular value for t is going to tell us what the x-coordinate is. So the way of sort of thinking about this is as time starts here at 0 and increases at a constant rate, the x-coordinates are going to start at 0, and the x-coordinates are going to increase. And they're not increasing at a constant rate, they're increasing at an accelerating rate, at an increasing rate, as you can see by the square. So let's come back to that. Let's look at the y values. So as time starts at 0 here and increases at a constant rate, the y values are just matching the values for time. So what that means is that if I was going to imagine, let's ignore the x-coordinate and let's just imagine it's always 0. And let's imagine time starting at 0 and increasing. The tip of my pen is going to represent the y-coordinate, and my finger is going to trace time here. So as time is going this direction, you can see the y-coordinate's going up. So as time goes that way, my y-coordinate should increase at a constant rate, because that's what this graph is saying. Okay, so as my y-coordinate's increasing at a constant rate, what's happening to the x-coordinate? If the x-coordinate was also increasing at a constant rate, I'd not only be going up, but at the same time I'd be going over at a constant rate, and you put those together and you'd end up having a line. But what's actually happening is y is going up at a constant rate, but the x-coordinates are getting larger and larger, faster and faster. So that's a good indicator that it's going to trace out a curve that is roughly like that. I don't mean to suggest that there's a horizontal asymptote here, because there's not. Okay, so this visualization technique, it should give you, in many cases, kind of the rough picture that gets created. It's not going to do a lot for giving you detail. So if you need to figure out the detail in particular regions, you'd want to actually plug in specific values of t to double check, like what points does the curve actually pass through. But if you're interested in figuring out the overall shape, this is a fine way to do it, thinking about how do x and y change independently. Combining the two equations to produce a regular Cartesian equation is a spectacular way to know what the curve looks like. But a lot of the power of parametric curves is that you can make all kinds of interesting, crazy paths that don't convert into a Cartesian equation very easily. So in the beginning, these are going to work just fine to convert, but later on, they probably won't. So let's do a couple more examples using that same way of thinking. Okay, so this set, you could also obviously just substitute x in for t, and you'd have y equals x squared. But let's pretend we didn't do that. Let's think about this separately, how each axis of motion is being controlled separately. So if time starts at 0 and increases, my x-coordinate is going to increase at a constant rate like this. Meanwhile, my y-coordinate is going to increase, but not at a constant rate. It's going to start slow and then get faster and faster and faster. And those are happening together. So it's going to start off like this, but then my y-coordinate is going to go up. Here, let's actually piece it out like this. So for every step horizontally that my x-coordinate is taking, my y-coordinate is going up by a greater and greater amount. So that's sort of another way of capturing the idea. And again, I've only sketched for t greater than or equal to 0 here. You would also want to think about negative values of t to produce the full parabola. Let's do another one. So in this one, the x and the y values are both the same. So if you imagine making a data table, no matter what the value of t is, it's going to produce an x value that's the same as the y value. So right away, we know that this should be the line y equals x. If you wanted to think about it in the way that I've been suggesting, we have an x-coordinate that starts out as time increases at a constant rate. The x-coordinate starts out increasing slowly but accelerates. Meanwhile, the y-coordinate is doing the exact same motion but in the other axis. So the y-coordinate starts out at 0, starts increasing slowly but at an accelerating rate. And if you imagine them doing that at the same time, I'm going to have a point, and you imagine sort of the intersection. So as my fingers are going this way, we're imagining that there's a point whose y-coordinate matches here and whose x-coordinate matches here. You'd have a point here that's tracing along y equals x, but it's going to start slowly as it's moving up the diagonal, and it's going to go faster and faster and faster. So the actual motion of the point starts slow and accelerates out that direction. This is a case where I've actually drawn the complete graph for all values of t. Because think about what happens when you plug in negative values for t. When you square them, it still gives you positive values for x and y. So if I was going to graph what happens as t starts at 10 and then goes down to 0 and then continues down to negative 10, I'd have a point out here that comes and then decelerates as it approaches the origin, touches on the origin when t equals 0, and then accelerates back away again. What's going on with this one? Well, let's start at t equals 0, which seems like a convenient point to start plotting our curve at. So when t equals 0, the x-coordinate is 10 and the y-coordinate is 0. So let's put that out here. Okay, so now the question is, as t increases, what's going to happen with x and y separately? Well, I can see that as t increases at a constant rate, the x-coordinate is going to decrease from 10 down to 0 and beyond at a constant rate. So as t goes up, my x-coordinate is going this way at a constant rate. Okay, meanwhile, as t goes up, my y-coordinate is increasing at an accelerating rate because it's t squared. So my y-coordinate is going this way faster and faster. So if I put those two things together, I've got seemingly a parabola, but whose vertex is here at 10. If you imagine t going towards the negative numbers, so let's say negative 1, for example, I have 10 minus negative 1 would be 11. So in other words, as t is decreasing, my x-coordinates are increasing. And the y-coordinates are doing just the same thing, because when I plug in a negative value for t, it squares. And so I'm going to end up getting the same y value as I would for a positive value of t. So, in summary, as the t values are going negative, the x values are going this direction at a constant rate, and the y values are doing the same thing that they did on the other side. So that gives us the other half of the parabola, and these are supposed to be symmetric with each other. Let's look at this set of 3. So here I've got a kind of trivial parameterization of y equals sine of x, because x is just equal to t, and then y is equal to sine t. So that's your kind of standard sine curve. And for all of these, I'm only going to graph t greater than or equal to 0. But if we were graphing all t, it would go out this way. Okay, so what changes when I have x be t squared instead? So the y says t starts at 0 and increases at a constant rate. The y values are still oscillating between -1 and 1, the way that a sine function does. It's just that in this version, as they were doing that, the x value is moving moving right at a constant rate. Here, it's going to do that same thing in the y values, but the x values are going to increase at an accelerating rate. So you're going to end up with something whose rough shape is like this sine curve that elongates that way. And I'm sorry for the imprecise drawing here. It never exceeds the bounds -1 and 1 because it's still, the output for y is still just a sine function. So it's still between -1 and 1. Conversely, in this case, the y values are doing the same thing. They are oscillating like this. But the x values, as time increases, let's just sketch this for a minute. So if this is the time axis and this is the x-axis, square root looks like this. So as time increases, and then here's the line y equals x. So as time, well, it's like a little bit imprecise around here. As time increases, the x values are definitely going up, but they're going up more and more and more slowly in a certain sense. So I'll have a sine function, but the sine function is going to get more and more compressed. I think it's worthwhile for me to show you what this looks like in Desmos, because it's great for you to be able to do this yourself in Desmos. All right, here we are. So you can't use x as your function name because that's reserved for something special in Desmos. But if you wanted to, you could say like p, well, you could just name your functions a and b and just remember that that means x and y. Or I think a little bit better is p, and then if you do an underscore and then x, and then press the right arrow key, that will give you an equation. So let's make, and the way I think about this is it's like the x-coordinate of a certain point. And here I'll do p and then underscore y and then the right arrow key. And then let's make this sine of t. Okay, so right now it's graphing these two things separately, but what I want it to do is graph the parametric equation. So have some parentheses and then say p underscore x of t and p underscore y of t. And then you can specify the range for t. So let's start at 0 and let's go up to like 10. Like 100. And so you can see that's a standard sine curve. But now let's make this be t squared. And you can see what I'm saying. Like here it's stretching itself by quite a bit. If I make this the square root of t, now you can see that it's compressing and compressing and compressing in the way that I suggested. You can do another kind of neat thing. So this will show you the full curve for all the values of t between this lower and upper bound. If you want to actually watch an animation, let's do the same thing. Let's have parentheses and then p subscript x, except this time let's use capital T, which is going to be just our own variable. You could call it something else if you wanted to. And then let's add a slider for t. And let's say t is going to go from 0 up to like 30. So now you can press play, and you can watch what happens as t goes up, and you can watch your little guy move around there, which is lots of fun. Like, I recommend that you play around with this. Let's do one last example. Let's say x is x times x minus 4, and oh, sorry, these are all t's. It's getting late at night. X is t times t minus 4, and y is t times t minus 6. So if I graph each of these separately, they look like this. So for the x-coordinates, I know that when t equals 0 and when t equals 4, the x-coordinates are going to be 0, because that's the roots of this equation. Same thing for the y-coordinates. When t is 0 or t is 6, that's where the y-coordinates are 0. So we can think about these kind of critical moments when we either hit the x or y axis at different times. Let's start out at t equals 0. So we know that at t equals 0, both x and y are 0, so our curve starts here. Let's think about what happens as we go from time equals 0 to time equals 2. So I see from this graph that the x-coordinates are going to be negative, and that they're going to be decreasing until they hit something. And we could figure out what that is pretty easily. So the x-coordinates are going to be going that way as time is approaching 2. The y-coordinates are also going to be going negative until time is 3. So they're both going to be going negative. So I know it's going to be sort of headed out this way. And you should think about sort of how fast are the x-coordinates going down compared to the y-coordinates, because that's going to tell you, are you sort of headed out this way or are you headed out this way? I've suggested that they're the same, but they're actually not. But let's just sort of rough out the curve at the beginning, and then we can go back and think about it harder. So at t equals 2, it will be kind of somewhere, this is t equals 0. At t equals 2, it will be somewhere in this third quadrant. As t goes from 2 to 3, what's going to happen is the x-coordinates are going to start increasing again, but the y-coordinates are going to continue to decrease until their most negative point. So the x-coordinates are going to start coming back this way as the y-coordinates are going down, until we get to some point here at t equals 3. Okay, so let's keep going. Now as time goes from 3 up to, as time goes from 3 up to 4, the x-coordinates are going to continue to increase until they hit 0 again. So the x-coordinates are going to continue to go until we hit the axis. Meanwhile, the y-coordinates are starting to, the y-coordinates are starting to increase, but they're still negative. So I'm sort of headed back this way. Okay, as time goes from 4 to, let's say, 6 here, I see that the x-coordinates are now going to continue to become more and more positive. So the x-coordinates are going to go this way. I don't know what the y is doing, but the x-coordinates are going to go this way. Meanwhile, the y-coordinates, starting at, we said this was t equals 4, the y-coordinates are eventually going to hit the x-axis, because their coordinates are going to become 0 at time equals 6. So it's going to be sort of like that. And then as time exceeds past 6, both x and y are now positive and increasing, and so we're going to have something going on like that. Okay, so a lot of the overall shape here is probably a little bit wrong, but the things that we do know are correct are that we're headed sort of diagonally this direction, but we don't know quite in which way, and it's also probably not a line. But we know that at some point, the x-coordinates turn around. Not at some time, at time equals 2. We know that the x-coordinates reverse while the y-coordinates continue to go down. Then at time equals 3, the x-coordinates keep going in that same direction while the y-coordinates have reversed. At time equals 4 is when the x-coordinates break into becoming positive. The y-coordinates are still negative, but they're still going up. And then at time equals 6, that's when they're both positive and increasing. Let's just look at Desmos to see what this actually looks like. So here we go, and we didn't actually do too badly. So you can sort of see the moments that I'm talking about. Let's look at them here. Let's go up through t equals 6. So when t is 1, 2, so t starts here at 0, and then when we hit t equals 2, we've hit this point where you can see it's the smallest possible x-coordinate, and the x-coordinates are turning around. Now at time equals 3, you can see that we've hit the lowest possible y-coordinate, and now the x-coordinates are continuing towards 0, and the y-coordinates are also increasing. At time equals 4, we've hit the axis, and so x-coordinates are becoming positive. And then at time equals 6, that's when now we're continuing out this way. And let's zoom out a little bit. So this is very interesting. It really looks like this is linear. It's actually not quite linear, but it's probably approaching linear. Maybe that's enough for now. But my takeaway point for you is that there's usually several different ways to think about parametrics. I think it's nice to get the rough overall shape by thinking about the XY motion independently. But for detailed problems, it pays off to think about the special values or critical values. And those are places where like x is at its smallest or x is at its largest, or where x or y switch from being positive to negative, because that's a place where your curve would turn around. So all of those things are worth paying attention to. I hope that this was helpful. Enjoy your studying.